Chapter 20, Part 1 on Nuclear Chemistry. So some elements undergo this process of radiation. We call these particles radioactive. What happens is nuclei will actually transform into another element. So normal reactions are just rearranging atoms and to form new compounds. In these reactions, we actually turn from one element into another element. We call this radioactive decay or radiation. So elements that do this has to do with the stability of the nucleus itself. So the stability of nuclei is due to something called the nuclear force or the strong force. It's the force of attraction between the nucleons being the protons and the neutrons. It's only for these substances because they're very close to each other, they're very short distances. And this force compensates for the fact that protons repel other protons because they're both positively charged. And so this force compensates for that and gives a stable nucleus. What we found is that nuclei with certain numbers of protons and neutrons are more stable than other. And if your nuclei is unstable, so it has a different number of protons or neutrons, then they tend to undergo these nuclear reactions, which turn them into other elements. So the current model of the atom has something called the shell model of the nucleus, which is just this theory that protons and neutrons are arranged in different levels, like electrons are arranged around the nucleus. But they have different numbers it's not the same numbers as electrons. So the numbers of protons and neutrons that are stable, we call these magic numbers. It's just how many particles we have in your nuclei that are most stable. So these are the magic numbers of protons. You don't have to memorize them. And then the magic numbers of neutrons as well. So what we found is if your element has these magic numbers, then they tend to be very stable. And if not, they tend to undergo this radiation process until they get a product that has these magic numbers that are very stable. So if you were to plot the number of protons, which is the atomic number, versus the number of neutrons for all stable substances, they end up forming this pretty linear line. We call this the band of stability. So this is the region where your protons and neutrons, those numbers, that combination leads to a very stable nucleus. So if a given element has a proton and neutron number that doesn't fall in this band, they tend to be unstable and then undergo some sort of radiation process. So for a nuclide, which is just your nucleus, that has an atomic number up to 20, so atomic numbers, which is hydrogen to calcium, they tend to want a ratio of 1 to 1. For every 1 neutron, about 1 proton. As we get a little larger, we want to have 1 neutron to about 1.5 protons. Okay, then as we get larger, as we get above 83, there's no stable nuclei because there's just too many protons that repel each other and that strong force can't override that any longer. So if it's 83 or less, they tend to have at least one stable nucleus combination of protons and neutrons. There are a couple of exceptions, but this is a general trend. So there's two types of nuclear reactions. Radioactive decay is when you have one nucleus that spontaneously disintegrates or turns into a different element. We call this unstable nucleus the parent particle. It is the substance that is radioactive. What's going to happen is it's going to turn into a new element. We call that the daughter, which hopefully is more stable than what it started out as. And in the process, it gives off some sort of radiation. Radiation is made up of different particles. We'll talk about all the different types in a minute. The other option is nuclear bombardment, where your nucleus, your parent particle, is bombarded or struck with another substance. So either another nucleus or some sort of radiation. And then the two things combine to form a new nucleus. Again, the daughter, hopefully something more stable. So So for a nuclear equation, we do them a little differently than we do normal reactions. What we have to include is the nucleus information. So we do the isotope symbol or the nuclide symbol we talked about last semester. So for the nucleus symbol, you start with the element symbol. So in this case, U is uranium. The mass number, which is always going to be given after, so you put the element dash some number, that's the mass number of that nucleus. Going to go on the top as a superscript, and then on the bottom you write the atomic number, which you can find on the periodic table. So for uranium it's 92. And we do that for every component of our reaction. So for example, if we have a reaction with uranium-238 that undergoes a nuclear reaction. So in this case, we're talking about alpha particles. We're going to talk about all the particles in a second. For now, know that alpha has a mass of 4, and it has 2 protons, and its symbol is the symbol for alpha, which is like this little fish. That is your radiation. If we know that, we can also figure out the daughter particle, what it turns into, because of the law of conservation of mass. My uranium started out with a mass of 238. The radiation had a mass of 4, so the new thing that's left over has to have the remaining mass. So in this case, 234. Same thing with your atomic numbers. Your uranium is 92, your radiation has 2 protons, so what's left over has to have the remaining 90. In this case, that's thorium. So in this case, your uranium is turning into a new element, thorium, giving off this radioactive particle in the process. So there's 6 types of radioactive decay. So the first one is called alpha. Alpha symbol looks like that. Mass of 4 and 2 protons. Something else that has a mass of 4 and 2 protons is the same thing as helium. So usually those two things are interchangeable. So in this case, radium-226 is a substance that can undergo alpha decay. So your radium is going to spit off an alpha particle, and then what's left over is going to have the remaining mass and the remaining protons. And in this case, that turns into radon. So it's going to spit off this one little particle, and then what's left over is now a new element. The second one is beta. So beta is a high-speed electron. It has no mass and a charge of -1. The symbol is a B. Since we also know this to be an electron, we can also do E as the symbol. Essentially what's happening is one of the neutrons is turning into a proton. Neutrons have a mass of 1, but no charge. And the symbol is neutron. So when that turns into a proton, mass of 1 and 1 charge, the other thing that's going to result, in order to balance out, has to be this electron. That's the only thing that can happen that's going to have the law of conservation of mass. So what's going to happen is one of the neutrons in the nucleus turns into a proton. So the atomic number is always going to go up. So carbon-14 is going to spit off one of these electrons or beta particles. And then in the process, it goes from having 6 protons to 7 protons, which is nitrogen. The mass number doesn't change because you're going from one particle to another particle, so you still have 14 total. It's just one is turning into a proton, so your atomic number goes up. Okay, the second one, or the third one, is positron, which is equivalent to a electron in all things except that the charge is opposite. So instead of being -1, it is +1. So it's no mass but positively charged. And this is an error. This should be the same as turning a proton into a neutron. So my proton, 1 mass, 1 charge, turning into a neutron. The other thing that has to remain has to have a positive charge in order for it to abide by the law of conservation of mass. So technetium, which is 4395. What's going to happen is its atomic number is going to go down, but it's also going to release this this positron particle over here. Okay, the next one is electron capture, which is a bombardment type of reaction where your nuclei actually picks up an electron from itself. What's happening is a proton is changing into a neutron just through a different way. So the proton is adding an electron or a beta particle, turning into a neutron. So the atomic number again is going to go down, but the mass number is going to stay the same. So for example, potassium adds this electron or beta particle. Mass number stays the same, but the atomic number goes down, which is in this case going to be argon. Okay. Gamma is a little different because gamma is just extra energy that's being released. The symbol is a little y, it's like the Greek letter symbol for gamma, has no mass and no charge, so it's 0, 0. Elements that do this are called metastable, so they don't change into different elements, they just sort of release out extra energy. So if something is metastable, it'll have a little M next to it. So it's going to release this gamma energy, which is just a source of radioactive energy, and still be the same element, but the same, not TC again, 43, sorry. But it's just more stable. The last one is spontaneous fission. So fission is when one nuclei splits apart into multiple smaller nucleus. So in this case, uranium splits into yttrium and iodine, and in the process also releases 4 extra neutrons out. So we're just breaking apart into multiple smaller things. So how do we know what's going to do this process? We can look at the ratio of protons and neutrons and see if they fall outside of that band of stability. If they are to the left of the band of the stability, which means that they are larger, they have more neutrons than they need. So they tend to undergo beta emission. Oops, nope, 1M. That's going to reduce the proton to neutron ratio because we're going to produce more protons in this beta emission process. To the right of the band of stability, they are lighter than the stable counterparts. So we want to increase that neutron to proton ratio. We can do that by doing positron or electron capture. In both of these, we're going to get more neutrons and have less protons in the process. If they're very heavy, greater than 83, they'll tend to undergo alpha emission. So if we have these two, so we've got calcium, 47. So in this case, 47, we want to compare that to the stable one, which is the one on the periodic table. So calcium stable is 40. So this is heavier, which means we want to undergo beta. For aluminum, the stable on the periodic table is 27. So this is lighter. We're going to undergo positron or electron capture. So this is just an easy way to kind of predict what it's going to do. We also have some that undergo decay series where one reaction doesn't produce a stable nucleus. So it just continues to do this over and over and over again until it forms something stable. There's a few found naturally. Uranium-238, for example, undergoes a whole series of alpha and beta decays until it ends up with lead-206, which is a stable nucleus option. Okay. Ernest Rutherford also discovered that we can do these reactions on purpose. We can actually take two smaller things and bombard them and create a larger one. This is called transmutation. So nitrogen and helium will produce a larger element, oxygen. We do this with something called an electron accelerator or a cyclotron, which just makes elements move very, very fast so that they can bombard each other and collide at the nuclear level. All elements greater than uranium, so transuranium elements, were produced this way by taking smaller elements and combining them with other elements and creating a nuclei that's very strong. However, all of these elements are radioactive. They're not stable. They turn immediately into decaying into other things, so they all are man-made and very, very short-lived because they are not nuclear stable. So right now we've done this up to element 118.